So in this example, we are going to see a very small example by using the iris dataset. You are already familiar with iris dataset. Okay, so when we move on to our data and when we move on to the samples and data, and you have this iris dataset. So in the iris dataset, if you see, one second, data, right. So here you could see all the IDs. You have different labels. One is setosa, okay, and then you have virginica and versicolor. So basically we have three different classes in this data sets. Okay, we have 150 samples, 2 special attributes and 4 regular attributes. Okay, so this is the data which we are going to deal with. Okay, so here we have our data set. We have taken the data set and we have actually applied a cross validation. Okay, so there is a operator called cross validation in Rapid Miner, so I'm using that, so I will tell you what is basically happening in this cross validation. So when I open this, it's a simple process. It is nothing but you are actually dividing your data into training and testing. Okay, so in the training, what are you doing in the training? Basically you are taking, see here, when you look at the cross validation parameters here on the side, you could see that you are actually doing a 10-fold cross validation. And sampling type, there are different type of sampling type, but as we have not learned all the different type of sampling types, we are simply going for, because we have actually touched upon this in the data pre-processing. Okay, in the data pre-processing we are actually touching upon it, but we are basically learning about a top-down approach and a cross bottom-up approach of sampling, but we are not going into detail. So that's why I'm not touching on all this different type of methods. So we are just taking the automatic one. Okay, so we are basically taking the number of the folds as 10 and the sampling type of automatic, and we are leaving all the other things as such. And when we look at this KNN, you could see that the K nearest neighbors is basically taken as 5, and the measure type, we have different type of measures, but by default one is mixed measure. We are just taking it. As we have taken mixed measure, we are taking the Euclidean distance as mixed Euclidean distance. That's all. So you don't have to worry much about it. So here when you look at this is basically going from the model. So this is your model. From the model output to the model to the model input here for the apply model. And apply model, you already used this, so we have this apply model, and the testing is connected to the testing. That's it. Okay, so this is your testing data and this is your training data. And the labels, see here, the labels are connected to labels, and the performance is basically connected to the performance output, and the output is testing is connected to the example set. Okay, it is actually connected to the testing set. This is how it would work. Okay, so if you want to go back, you have to click on here, and when you look at here, the model output is connected, example, the testing, the performance, everything is connected separately. If you don't want to, you could just just take the needed data. That's it. Okay, so when I run this, if you see here, you could see that, okay, so this is basically called as a confusion matrix. So this is what I wanted to tell you. So this is a confusion matrix. So basically confusion matrix just says that how many of the true data, so it just gives you an accuracy. Okay, so the measure which we use here for in terms of the confusion matrix is nothing but, so as you see, like matrix, it is a matrix only. Okay, so what basically does is that true number of setosa samples are 50. Okay, and how many of them has been predicted as setosa itself? Yes, 50. How many true samples are there? 50 samples. So 47 plus 3, basically 50 samples are there. In that, versicolor has been correctly identified as versicolor is 47, and wrongly classified is basically, it is 3 of them are basically classified as virginica, which is wrong. Okay, so 94% accuracy. Here we have 100% accuracy, here we have 94% accuracy, because we have some error rate in this. And now when we look at the virginica, basically how many virginica samples are there? 50 samples, because in our iris data set we know that we have 50 setosa, 50 versicolor, 50 virginica. So 50 is there, but in that 50, what happened? Few of them has been misclassified as versicolor. Okay, so we have 94%. So this is the precision and this is the recall. So this precision, recall, so we will see about this precision and recall in the coming classes, or I will put a video on that, so you will be able to understand that. So this is the confusion matrix. So this matrix will just tells you what is the actual data and what is the predicted data. So the relations, so how many of them are the actual data, how many of them has been actually been predicted as correct, actually not been predicted as, or has been predicted as wrong. So this performance, okay, this matrix is basically called as a confusion matrix. Okay, and that's also here also you could see that how many of them are truly classified, how many of them are. So this is the confusion matrix if you see. Okay, so this is what it is. So this kind of a complete understanding about your data could be identified by this. So when you look at this, this is how the values of each and every one, this is the output of your cross validation. So in the cross validation, basically what happens, each and everything. So the confidence of, you are considering, what is the confidence of each and every class. So for our, so setosa is identified as setosa. So it is 1, these two are 0. So like that. Okay. So when you take a wrong one, if you look at that, so how closely it is identified, so that value will be basically given to you. 1 second, setosa was, I'm unable to see here, but yeah, so see here when you look at this here, so this is the Versi color and this is actually Versi color, but it is actually predicted as Virginica. So it is 0 and there is a, so how much similarity is there, so that similarity measure is basically shown here. Okay, so all these details could be easily identified in this data. Okay, this is the original data set, this is your KNN, this is your example, this is your original data set as such, and this is the performance matrix, and this is your cross validation output as such. Okay, so this is one simple example for that. So this is another simple example of confusion matrix which is already there in the given set of examples which is already there. So I'm just taking that. So they are basically taking a example data set. So when we take the example data set here, the number of the attributes is basically 2, and the example samples of 500 samples are there, and we are going for a target function like there are so many different functions in that multi-classification, right? So this is what is done. And when you look at the cross validation, so they have used the nearest neighbors. Okay, there is a function called nearest neighbors. Okay, so they have just taken it as the KNN itself and renamed as nearest neighbors. Okay, and the model is given to the model, and the apply model, this is actually the apply model, but they have renamed it as model applier, and then classification performance they have done it. So that's all. So it's a simple KNN algorithm only, and when you run this, you could see that they have gone for 2 different measures. One is a kappa measure and one is the accuracy measure. That's all. So they have gone for 2 different measures, and that we already know, we only know this accuracy measure as of now. We have not learned about the kappa measure. So here also you could see that how each and every attribute is basically considered into correctly classified or not. So this accuracy is basically very lesser, 60 to 59%. The accuracy is lesser. So this is one example. So this is how you could utilize this cross validation as of now. So in this experiment or in a lab, we are just trying to understand something called AUC. It is basically called as area under the curve. Okay, so when you look at this, there are false positive and the true positive, which we have already seen in the confusion matrix, right? So this purple line basically shows the perfect classifier. So if you have an x-axis and y-axis with the positive, false positive rate and true positive rate, if you look at this purple line is the perfect classifier. So which one is the best out of 1, 2, 3, 4? There are 4 different classifiers. One is blue, one is orange, one is green, one is a random classifier. Okay, so in all this, which one is the best one? Blue will be the best one because it is more closer to the perfect classifier. Then comes orange. Orange is okay because it is when considered to the blue, it is actually okay but not that closer. and then green is fine, it's kind of a linear classifier. Okay, we will learn about more of that in the linear regression. Okay, and this is a random classifier. So whenever you have an area under the curve, so this is the perfect curve, this purple line is a perfect curve. So as we have more number of area, we have more area under the curve, then we will say that that classifier is basically the best. So keeping this in mind, I'm going to rapid miner and showing you an example. Okay, so here in this example, they have actually taken this random, some, you don't worry about, some classification technique is taken, and then again we have 500 samples, number of attributes 2, and then when we look over to the cross validation, we have this training and the testing divided into training and testing, and the training is basically you have actually taken as 80, and then the testing, if you see, they have actually taken as 20, and in this they have used this SVM is another classifier, which is classification algorithm, which is nothing but support vector machine. So support vector machine is basically wonderful, its theory and its algorithm is beautiful, and it is very commonly used. Another classification algorithms, support vector machine, and libSVM is its corresponding model, which has been built by the library of the SVM, which is built by the rapid miner, and you have all this in your Python studio and everything, and you have applied a model, and you are using a binary classification because you need to classify specifically whether it falls into which class. Okay, so when you run this, you could see that you have a positive class and you have got a negative class. So this is why it is a binary classification algorithm. So you have this true negative, you have true positive, you have false positive, false negatives. So when you look at this, so 432 plus 3, so 435 samples are basically negative, but 3 of them are classified misclassified. But when you see here, 28 plus 37 are positive, but it is misclassified a lot. So here this is basically wrong. So when you see the ROC curve, okay, so one is positive and one is negative. Okay, so when you see the which one is basically the negative one, so negative one is basically good because the area under the curve is basically better, and when you look at the positive one, basically the area of the under the curve is actually lesser, so it is having a less accuracy. This is how you will interpret that or inference that. Okay, so this you have to identify. So the class, when you look at the class prediction, each of the class prediction, okay, fine, it's okay, but otherwise when you look at the recall, so your accuracy is still better. Okay, the accuracy is 93%, but with there is an error rate of minus 2.5%. Okay, so this is how it will basically done. So when you look at this is the confusion matrix, if you see, so the same thing only, they have actually, this is exactly the same thing, 432, 28, 3, 37. Okay, they have just described it in this particular way. That's all. Okay, so this is one particular example which I wanted to know, tell you, because this is very useful when you look at the, when you do your projects, this AUC curve will be really helpful for you to come out with. So another example here which you will see is about the okay, we'll first see about the simple validation. So in the simple validation, if you look at this, there is a training and the testing, but at this training and testing, basically they have a linear regression operation. So this is basically a classification by linear regression. So you have given this, and then you have basically done the classification by that. Okay, so when you look at the model, you have a linear regression model which is used for classification. Okay, so this is how you have done. Then you have actually given that output for the testing. So all these things are basically possible. So so when you look at this, the accuracy is basically 82 points. So it is actually even more, you have done even more detailed analysis on this. Okay, so this is one thing, and another one is basically the fixed split validation. Here what basically you do is that you will use a fixed number of example for either the training and the testing data set. So this is exactly the same thing, but you are using a fixed number of data set for the training and the testing. For the training and the testing, you are basically using a fixed fixed data set. Okay, that is basically your fixed test. This is shuffled sampling. Okay, so this split is basically absolute. Okay, your split here is basically absolute when you look at here and this is relative. Okay, hope you're able to understand. So in the simple validation, you use this relative split, and in the fixed split validation, basically you use the absolute. So it is actually, you know, fixed number of values for both for the training set and for the data set, for the test set. Okay. And there is another example which is given here. This is all part of the examples which are there in the in the rapid miner, which is already there. So here, if you see, for the model, for the training itself, you have actually used the naive Bayes. Okay, naive Bayes is another classification algorithm which is already available, and for the model, you have actually, you know, you have modeled the model by using not only with the training but also with some extra data set. Okay, so the test set is basically, you know, separately loaded. So this is your training data set and this is your test set. If you look here, this is the test data set. It is actually loaded separately. Okay, but just make sure that both your training data set and your testing data set should have a same set of, you know, labels. So that labels has to be there. So this is also possible. So all these different ways are basically possible. So try to explore a little bit more so that you will understand the various ways in which you could do the classification. You're getting it? So that is one thing wherein which you could try and understand different models. We are not looking over to the initial models because this is all about your regression and decision tree and everything, because we have not gone through it. So I think we are good to go with the rapid miner. So that's all about it. So just have a look. So also you could just explore the templates. Okay, there will be certain templates which are already there. So in the templates also you could see some examples. So I will show you one example in the market fraud detection. So in the market fraud detection, this is the medical data which is used, like, you know, so the amount predicted, you know, so many values are basically given here. So the amount paid. Okay, so this is about your fraud detection, you know, like, you know, maybe the insurance or something like that, some data. So basically if you look at the classes, you have 2 and 4 classes. So this is basically a binary classification, and now when we look over to it, so you are actually retrieving the data. So it is all given. So don't worry about the GPT algorithm here. This is a gradient boost algorithm, boosted trees algorithm. You don't have to worry about it. So instead of that, you can use any of the classification algorithm which you know, like the naive Bayes, or, you know, the KNN algorithm, or simply the nearest neighbors algorithm. Any of the algorithm or SVM or anything could be used. So you are actually removing all the correlated data here. So you are doing a pre-processing here. Then you are applying the cross validation. So when you look at the cross validation, this is basically a training and the testing algorithm. You are taking the sampling, you are applying the algorithm. Instead of this algorithm, you can use your algorithm, whichever you want, and then you are applying the model. Then you are, you know, seeing the performance of GPT. So instead, if you are using some other algorithm here, you will get the performance of that particular algorithm. So it's just drag and drop and, you know, plug and play here, and then you are actually finding out the results. Okay, so when you look at this example, let me see, I think it is getting done. Yes, it is done. So if you look at the results, so here also it just gives you the 2 differences, a confusion matrix which is given, and 82% accuracy you are getting. So the classification error matrix is given here, AUC is given here. So precision, recall, specificity, everything is basically given separately here. So that's all it is. So if you want to try different type of algorithm, so this is your GPT. So in your GPT, basically, you know, each and everything could be seen. So amount paid, up to date, and each and every tree. So this many number of trees are basically generated. So for each and every tree, because this you will understand when you learn about the decision trees. So that's why I'm not going that detail into it. But otherwise, you know, this is how it will look like. So this part you will be able to understand. So instead of your GPT, basically you could use any of the Neighbour algorithm or anything like that, or KNN algorithm, and you can replace those algorithm here, and then you could try it. Okay, so this you could just have a look over to it. So that's all about the various algorithms. So there are, again, you know, certain set of examples which are given over there. So just explore, try to explore a little bit more, and try to understand the different ways in which you could do the classification in a rapid miner. So that's all as of now. So have a nice day. Thank you so much. If you have any doubts, you can always get back to me. Thank you.